Chapter 33 homework. It's on electromagnetic induction. So problem 4, saying find the net flux. Well, this is 2 Tesla into the page. This is 1 Tesla out of the page. The area of each of these is 0.04 square meters. So essentially I could take the net flux. So that's kind of what I did here. And got 0.04 Tesla meters squared, or 0.04 Webers, and that's into the page. For problem 11, you have a radius of, a resistance of 0.2 ohms, a diameter of 10 centimeters, so that's a radius of 0.05 meters for something, and it's asking you what the EMF is, or the induced current rather, and so whether it's clockwise, counterclockwise. So if this field, which is already going into the page, is increasing in strength at 0.5 Tesla per second, I is equal to EMF over R. EMF is equal to change in flux per unit time. So that's change in field strength times area. So kind of have derived this, took a little bit more time over here to do that than you might have to. So that's the dB dt, or d phi dt, pi r squared. That's 0.0039 volts divided by 0.2 ohms gives me that current. And to oppose the increase in x's, the induced field will be dots, so that would be a counterclockwise current. So dots on the inside, you can use a right-hand rule to figure out the direction of current along here. In this case, you've got dots already, so you've got the field coming out of the page, but it's decreasing in strength. So to oppose that, you also need more dots. So this is the exact same problem as question A. In both cases, you're going to need the same EMF, same amount of current, and in the same direction. So that would be also a counterclockwise current. Here, this loop, it's kind of hard to visualize, but basically it is in a plane. Ooh, that's awful. The page like this. So it's kind of hard to see that. I'll get rid of that. So you're only seeing the wire at the bottom and the wire at the top. So because of that, the BA cos theta, the A cos theta is 0. Because although we think about that, think about the area as being perpendicular to the face. So in this case, the area would be probably pointing out of the page, area pointing out of the page. Here the area vector is pointing either to the left or the right. So because of that, cosine of something at 90 degrees is 0. So I have no flux here, and whether the x's are increasing or decreasing doesn't matter. For problem 13, it says a 1,000 coil loop of wire, 1 centimeter in diameter, 5 times 10 negative 30 meters radius. So it says in 10, that should be 10 milliseconds. Not meters per second. So I will see what I can do about that. Nothing. Put that up there. Now you never know I screwed up. Anyhow, you get that this is 20 Tesla per second is the rate of change of flux. If you multiply that by the area, pi r squared, you get like 0.00157 volts, but there's 1,000 turns. Basically, each of those loops is going to create 0.0157 volts. So overall, it's going to be 1.57 volts. So I may have been off with my decimal at some point in describing the problem. I know this ends up mathematically to 1.57. Problem 14 says you've got a 0.2 ohm resistor in this wire, and it's asking you if you've got a 0.15 amp current, and this is 8 centimeters on each side, to find out the rate at which the flux is changing. So first, if I know the current and the resistance, I'm going to find the voltage. That voltage, known in magnetic circles as an EMF, is going to equal to dB dt times area. I know the area. And it's not 0.08 meters squared, it's 0.08 meters, parentheses, quantity squared. So I take the voltage divided by that, and I get the rate which it's changing. For 29, in this particular case, it gave you the flux. You can figure out the change the field strength. It gave you the change of field strength with respect to time. So you take the derivative of this to get this, and at 0 seconds, at 1 second, at 2 seconds, you can determine the current because it's that rate of change of flux divided by time. So 4 teslas per second. So basically that's 4 minus 4 times 0 would be 4 times the area. Here at 1 second, 4 minus 4 is 0. Here 4 minus 8 is negative 4. Again, I can multiply that by 0.04 meters squared, which is the area, and I get that current. So that's the instantaneous current. That would be continuously changing because this function also is dependent on time. This one was tough, so I apologize for this being like super scrunched. So this is a 100-turn coil, 0.04 meter radius for the coil, 0.5 millimeter diameter wire, so there's a lot of annoying units and things like that in there, made of copper, so there's a current going through it that's 2 amps. And basically you want to find the rate of change of flux. So the first thing I have to do, so I know the current, I've got to find the resistance. So to find the resistance of this, I've got to think about the fact that the coil has got a wire all the way around it, 100 turns, and it's made of copper. So I need to use a resistivity formula. So this is basically the resistivity of the copper, which I looked up from an earlier chapter. It's right there, 1.7 times 10 to the negative 8th ohm meters, or you could Google it. The length of the copper wire, not the length or the radius, like length of the coil, but the length of the copper wire. So the coil itself was a 0.04 meter radius. So if I think about going around the coil, that's fairly annoying. Do not want that dash line. So essentially what we've got here, if I made this a circle, made it smaller, you could think of each time that this is just awful. The current goes around this particular thing, it's 2 pi r is the distance. So I've got to find 100 turns. 2 pi radius of coil means that the length of copper wire I'll need is 25.1 meters. So 25.1 meters here, pi r squared, this is the radius of the wire, so the skinny wire, not the radius of the coil. So that gets me the area of that. That got me a resistance of 2.176 ohms. So now when I do that, I know that E is equal to I times R, 2 amps times 2.176 ohms, 4.352 volts. But that's for 100 turns. So if I look at E as the change in flux per time times area, I also have to take into account number of turns. So I get that total voltage, change in flux per time is what I'm trying to find out, pi r squared, that's pi r squared of the coil, and 100 turns. I think that's me 8.7 Tesla per second. So the really tough part about this problem, I think, is that you've got to recognize you need resistance and how to do that. That's resistivity. Then you've got to go back and figure out, well, the fact that, hey, I've got a coil, it's got 100 turns. So whatever voltage I get for that once I find resistance essentially is going to be 100 times as big as it would be if I just had one coil. And that would help you find the change in flux. So I will get rid of that red circle because it's annoying. For problem 31, like I said, I gave a little bit of explanation there. Problem 36, I did this way, which is a non-calculus way. There's a calculus way down here. There's an example in your book that's very similar to this. So that's kind of how I figured that out. I did not instinctively do the calculus way on my own, but essentially you've got something like this, and it's moving at 10 meters per second. It's a loop, and it's going away from a wire. The idea is this lower component of wire right now is at a certain distance, 2 centimeters from this 15 amp wire, so I should say the lower part of the rectangular loop. The upper part of the loop is further away, it's 3 centimeters away. So therefore, because they're both moving at the same speed, 10 meters per second, but the field strength is different at the bottom part than the top part, the rate of change of field strength and the rate of change of flux is different at this bottom part of the loop compared to the top part of the loop. Wherever the rate of change of flux is stronger is where we're going to see a bigger effect to push a voltage. That's the tough idea. So what I ended up doing is I tried to figure that out at the lower wire and the upper wire. So at this instant, the magnetic field at the top of the copper wire is found by Ampere's rule for a long wire, B sub r, 4 pi times 10 to the negative 7th, I, 2 pi r, r is the distance from the wire, so that's 3 centimeters. And it gets me 1 times 10 to the negative 4 Tesla. The bottom wire is stronger, 1.5 times 10 to the negative 4 Tesla. So I can find out the EMF generated at this point, by looking at this BLV. L is this length of wire, which is 4 centimeters. So 0.04 meters is moving away at 10 meters per second, and at this instant, it's at 1 times 10 to the negative 4th Tesla. So at that point, this would generate 4 times 10 to the negative 5th volts. This one being closer and having a stronger field would generate a higher voltage. So they're both generated in a way that they would oppose the change of that flux, but because this one's closer and has a stronger field at this instant, it's going to generate a stronger voltage. So the higher potential here is going to be at the left end of each wire. So really the left end of the bottom wire is going to push around this left end of the top wire. And I can figure that out. So that's the net voltage, which is the difference between the potential difference across both the bottom wire and the top wire. So at any rate, that's 0.2 times 10 to the negative 5th volts divided by the resistance of the loop, and that gets me the current. And that would be clockwise to oppose the net change in flux. I'm going to leave this way for you. 43. This is actually with a transformer. I only gave one problem with this, but you really should be familiar with transformers. They're really neat. The big idea is power that's going in should be equal to power coming out for an ideal transformer. Oftentimes it's a little bit less. There's heat losses, resistive losses, things like that. So essentially you've got the number of turns in the primary over the number of turns in the secondary is equal to the voltage in the primary coil over the voltage in the secondary coil. So I use that to figure out the number of turns. That's 12,500 turns in the primary. And understanding that you shouldn't lose energy in an ideal transformer, I get P times I initially would equal P times I, or V times I initially is equal to V times I at the end. So I get 2 amps in the primary coil. 47, tricky. The reason this is 3 volts and not 4 volts is because this particular piece of wire is moving. It has some of the resistance. So it's almost like an internal resistance of the moving length of wire. Otherwise, this would not be that tough of a problem. So we could figure out, said at this instant it was 100th of an ohm on each side. So the total resistance is 0.04 ohms. Find the EMF equals BLV, so 1 Tesla. Length of wire moving 0.04 meters, 100 meters per second, that's 4 volts. And you got a current of 100 amps. But since this length of wire is 0.01 ohms of resistance, you would lose that potential difference across there. I'm not that concerned about that if you didn't get this. So if you got the 4 volts, or I don't know, maybe you got a 0 volt across this, I'd have to look and see. That's okay. 7050 is also a really good problem. The idea here is that we have a push causing this. That's a mechanical push, force times velocity, and that would equal the power, and that's the power to cause this to be pushed. That equals the electrical power needed or expended in the circuit. So I'm going to set these equal to each other. So it's really important to recognize this is a power formula and that's a power formula. So F times V equals BLV, which is the EMF. To get the current, it's EMF divided by resistance, so that's BLV over R. So if there was nothing else here, I'd say that's B squared L squared V squared over R. But one of these V's cancels out. So we get that the force is going to be B squared L squared V divided by R. and that's 6.25 times 10 to the negative 4th newtons. For part B, it's asking about the power to push this, so force times speed. So it was moving at 0.5 meters per second. The direction of the induced current is going to be clockwise because in this enclosed area we're reducing the number of dots. So we're reducing the field strength coming out of the page. That means we want to oppose that by adding more dots or increasing the field strength coming out of the page. And that would, from a right-hand rule, result in a counterclockwise current. So to find the electrical power from this, we could either use E times I or I squared times R. We know the current. We know the voltage. That's fantastic. So either of these are going to work. So, and the EMF would be equal to BLV, the rate at which it's moving. So I've got 0.5 Tesla, 0.1 meters, 0.5 meters per second, that's 0.025 volts. Take that divided by 2 ohms, that gets me the current. V times I gets me the power. Lo and behold, the electrical power that's dissipated should be the same as the power that you're using to cause the thing to move. So, ta-da! Mechanics and E&M are not that different. This one we talked a little bit about in the conceptual questions. Gave you the inductance. This is a formula that you should know. We don't use it. We haven't used it often, but the EMF caused by an inductor is equal to the inductance multiplied by the change in current per unit time. So again, if this was infinitely high, you'd have an infinitely high EMF, or an EMF that would at least be equal to the voltage that's causing the change. But anyhow, from here we can look at the slope. So the di dt is 2 amps in 2 milliseconds. And so that's going to be something where we get 10 volts. Because this is a positive slope and the EMF points in the negative direction, it's a negative 10 volt. Okay, so that's pushing backwards. Here the slope is 0, so we've got a 0 EMF. And down here from 3 to 5 seconds, we've got a negative slope. So it's negative 4 amps over 2 seconds. And, sorry, so negative 2 minus 2 is negative 4. But we're multiplying that by a negative inductance in the front because we oppose that change, so that gives us a positive 20 volts. So again, it's basically the negative of the derivative of this would give us things. Over here, 77 is the last one. What I really wanted you to think about with this was the circuit and what would happen. So this is invariable, how you would get the current at time 0. Change in battery, basically the potential difference across the battery divided by R, the switch is open, for something like that. For C, the pattern that we would notice if we close this is the inductor would oppose the change of current. So normally we would think we would go from 0 to I sub O immediately, but the inductor opposes that. And because the rate at which it opposes things is based on the rate of change of current, as this current levels off, we oppose it less and less. So we get an asymptote up here, leading to I sub 0. I didn't assign part B. I want you to take a look at this. So I didn't think it was that important. We hadn't talked about it that much, but this is the calculus way things. Essentially, you have to go through to differential equation, separate variables, things from that. Okay? And I think that should do it. What can I do for you, Leo?
Good morning.